Right, hello everyone, it's the third episode in the Sensory Ecology series. We're all very excited, aren't we? I know I am. Now today we're going to look into a bit more detail on directional hearing, the actual mechanisms of directional hearing. And we're going to use that using a very specific study system, which I've... Oh, where's my whiteboard gone? Hang on, where's the camera gone? This is ridiculous! Right. Sorry.
Finally, got my chance. Benito doesn't know I can make a video all by myself, and I'm going to take over his channel, and I'm going to be a star. I'm going to live my dream. I'm going to be a YouTube phenomenon. Where do I start? Sensory. What was it again?
Oi! What the hell's going on? I told you to fuck off! What the hell? This is going to be an unfunny joke for the rest of the series now! God, what the hell? What? You need to take those stars! Oh my god, you little shit! I fall back as well! Oh! Ridiculous. God, I don't believe it. Oh, God, this is not happening again. Hello everyone! Right, here we are again. It's the third video in the Sensory Ecology series, and we're still on hearing, but today we're going to look into a bit more detail on the actual mechanisms of directional hearing. How do we know where a sound is coming from? Now, we've kind of partially answered that question when we looked at diffraction in our heads, right? So if sound comes from this direction, then that's going to create a sound shadow on the opposite side of my head. That's how we do it, but we're large animals, right? So the distance in arrival time, the difference between that ear and that ear is going to be larger in time than it would be a small animal. In fact, it's about 0.5 milliseconds, so it's still pretty small, but good enough for our nervous systems to compute. But most animals on this planet aren't as big as us. Most of them are insects and they're tiny. So how the hell did they do it? And that's what we're going to focus on today. So the problems of directional hearing, as we mentioned previously then, is this interaural time difference, the ITD, which is the difference in arrival time of sound between the two ears, and this interaural amplitude difference, and that's all due to diffraction around our heads and the creation of a sound shadow, right? There's also spectral information's a problem because the frequency composition of the sound arriving at the two ears may be slightly different. Yeah? And that's less of a problem most likely if you're a small animal and the distance between the two ears is pretty small. And that's basically what we're going to be focused on today anyway. So we don't need to worry about that side of it so much. For example, in insects, the temporal cues are in the microsecond range. Now that's way too small for the nervous system to compute. So how do animals get around that? Right? So we're going to look at crickets to start off, and you'll see by the end of the video that everything we've talked about will sort of link together somehow. We're mostly going to be focusing on flies and crickets. So let's look at the crickets first. And you can test this by doing various experiments where you block the tympanal membranes and rotate a sound around a cricket and measure its response. Okay, and do some neural experiments as well. It's quite easy to test. Okay, so crickets then have tympanal membranes on the tibia of their forelegs, okay, so their front legs. So the ears on their legs, that's a bit strange. So tympanal membranes are a form of pressure receivers that we talked about last time. Okay, it's the difference between the external and internal pressure which determines whether a signal is transmitted to the CNS and all that, right? Now, we also talked about last time how insects were the absolute kings of particle velocity receivers. So crickets have them as well, but they also have these tympanal membranes. That's what makes insects so bloody marvellous, right? Now, I seemed to suggest last time that there was only two types of ear, didn't I? So there was the pressure receiver and there was the particle velocity receiver. Well, that was a kind of a lie, I'm afraid, because there are various different kinds of pressure receiver. Okay, and we're going to be talking about them just now. Okay, so obviously there's a simple pressure receiver, which I drew last time. That's just where there's a single membrane, sound interacts with the membrane, makes it wobble. Difference between external and internal pressure will affect the impulse generated, right, the action potential. There's also this thing called a pressure difference receiver, which works in very much the same way, but here there are two tympanal membranes, and this is what's going on in our crickets. The tympanal membrane is connected to the tracheal tubules of that insect. Okay, the membrane's actually protected as well by some guard cells, which means as the cricket is moving about, it doesn't puncture its tympanal membrane when walking through vegetation. Okay, so this tracheal tube runs all the way around from one foreleg to the other. Okay, so at the other end of the trachea, there's another tympanal membrane, and it's, well, the name says what it says on the tin, so it's the difference in the pressure received by the two tympanal membranes which affect the directionality. Okay, so I've drawn a very, very basic diagram here of a pressure difference receiver. So let's see if we can make sense of it, shall we? There are two big words that we've got to sort out, and that's ipsilateral and contralateral. Okay, ipsilateral is the side in which the sound is coming from. Okay, and contralateral is the other side. Okay, so we've got sound coming from this direction, and it's hitting this membrane, this tympanal membrane here, right, on the left, on the ipsilateral side. So that's going to cause some force inside the trachea. Okay, so this is inside the trachea, very short trachea, but you get the idea. So that's going to create an internal pressure pushing it towards the contralateral side. So that's PI, internal pressure going that way. Right? Meanwhile, there'll be pressure. Remember, this is Newton's third law of mechanics, isn't it? Opposite and equal forces. God, I don't know what it is. But yeah, if you add a force that way, there'll be another force acting in that direction, right? From the external environment. Now, when that happens, if the sound is coming from this direction, then you'll get destructive interference here. Okay? These two forces will cancel out. Whereas here, this force and the internal pressure will reinforce each other. So you'll get constructive interference. So that's your directionality sorted then. Because that means you reinforce the signal on the ipsilateral side and denatured it, if you like, on the contralateral side. So there you go then, you know that the sound's coming from that direction. Amazing! So it's this asymmetry in the hearing sensitivity which produces these large directional cues. Brilliant. Okay, so that's the crickets. We're now going to move on, basically going to spend the rest of the video on this one species of fly which has been studied heavily by one of my lecturers, Daniel Robert. Okay? And that species is Ormia ocracea. Now you may think, blooming hell, flies, pretty dull animals, why the hell are we doing this? It's really annoying, isn't it? Well, not this fly. This is probably the most exciting fly you'll ever see in your life, right? It's a phonotactic parasitoid fly, and this is where the link comes in that I was talking about earlier. It's parasitoid, so that means it's half parasite, half predator. It lays its eggs on other insects, and when the larvae hatch, they probably feed on that insect, and then eventually it kills the host. Okay? And these flies are parasitoids on crickets. Right, so imagine the situation, right? It's dusk. A male cricket is chirping away trying to attract a mate, right? But inadvertently, he's attracting a female Ormia ocracea, full of eggs and wants to lay them somewhere, right? So, the female Ormia ocracea zooms in to the cricket, lays her eggs, and then it's there where the larvae will develop, and they'll feed on the cricket while it's still alive, right? It's brutal. And what's even more brutal is that the last thing that the larvae eat are the structures which allow them to produce the song. So the wings, basically. Crickets produce song by vibrating their wings together. Okay, that's the difference between crickets and grasshoppers, right? A little bit of trivia for you. So that cricket will carry on chirping while that larvae of the fly is eating it alive. Which I guess could be worse, because in that time that cricket could be achieving some extra matings and therefore increasing the chance of his genes going to the next generation. So, you know, kind of thoughtful I guess, but also a bit vulgar. So it's pretty clear then, seeing as though that these crickets are calling at dusk, the flies are using sounds to hone in on their hosts, right? But how exactly are they doing that though? Well, they have ears located on the coccyx of the prothorax, right? And I'll show you a picture of them now. Let's see a picture of them. Brilliant, thank you very much. Now, I talked about a normal pressure receiver. I've also talked about a pressure difference receiver. Is those ears that you just saw there any one of them? No, it's not. It's a third type of pressure receiver. The only type of its kind that's ever been discovered, right? And this is called a mechanically coupled pressure receiver, right? And this is basically like two normal pressure receivers joined together, if you like, but they're very, very different. So this is when you have two ears very, very close together. And using this mechanism, the fly can have increased ITDs, interaural time differences, and increased IADs, interaural amplitude differences. And that was one of the main problems that we discussed at the start of the video that animals need to overcome. Brilliant. And we'll look into the mechanisms of that in a second. But first, let's do some behavioural experiments. God, let's have some different lighting. Isn't that brilliant? It's almost as if we recorded this on different days. Anyway, so behavioural experiments then. The first thing that Robert and his colleagues did was looked at the threshold to generate a response in these flies. They played the flies loads of different songs, okay, of different frequencies. And they realised that the threshold was at its lowest at around 5 kilohertz. Now, that isn't exactly the optimum frequency at which these crickets call at, but it's near enough, okay? But it is out of sync nevertheless, so it's interesting why that is, and the reality is that we don't really know why. Okay then, so now, what do Robert and his colleagues do? Well, they set up an experiment. They do this experiment in a dark room, because obviously these flies are nocturnal. And what they did, hang on, I've had a better idea. Let me show you what they did. Now you're going to have to use your imaginations a little bit, I'm not going to lie for this one, because there's only so much I can do with a shuttlecock and a radio. Right, so what we're going to do is we're going to pretend that this shuttlecock is the fly Ormia ocrassia that was used in the experiment. And what the scientists did, they put it on a pedestal on top of everything, right? They then played the song of a cricket, right, on the other side of the room. So I'm going to put that loudspeaker here. So that's going to be playing a song of a cricket. Also in the room there were some cameras which were able to follow and pinpoint the exact X, Y and Z coordinates of the fly as it was flying. Right, so it builds up a virtual reality experiment. Okay, it was all very sophisticated, especially when considering this was done in the early noughties. Okay, so it was very technological. Now obviously these cameras that were tracking the fly's trajectories were in infrared because this experiment was done in the dark. So, let's play the song of a cricket. Brilliant, fantastic. So what the fly does then? Well, it wants to go near that cricket. So what it does, it's going to do a perfect projectile to the cricket. Now the actual trajectory of the fly is actually a little bit more complicated than that, which I can't show with a shuttlecock. As it reaches the speaker, it actually spirals downwards to the speaker, which shows even further that it's using sound to detect where it is. Okay, so now that we know that, we can start messing around a little bit then. So what we're going to do now is we're going to play the song and then see what happens when we stop the song midway through the fly's flight. Okay, so once this shuttlecock reaches a certain point, we're going to stop the cricket song. The question is, will the fly still be able to locate the speaker even if the sound is stopped halfway through? Let's see what happens, shall we? It does. Admittedly, it finds the fly less reliably than if the song was still playing, but it gets close enough, right? So that tells us something. That means if a cricket was able to detect a fly using its anal cerci, then that's probably not going to do much good because the fly would still be able to locate it, or it would be able to hang around that cricket until it started singing again, in which case it would be able to pounce. So this shows that these flies have a 3D spatial memory. So that's pretty cool. So now Webber and his colleagues wanted to find out what would happen if there was more than one cricket present. So they introduced another speaker. Here. Okay. So in this experiment then, one cricket started singing. So let's have the old song. Right, and the fly moved towards it, but this time, once the fly had gone past a particular point, that song stopped singing, whilst this one started singing. See that? Now, they probably sounded very similar, but we're having them different just so you can distinguish between the two, right? So, what happens then? So, well, if it hears the sound on the white radio to start with, it's going to move towards it, right? It then changes its trajectory. So therefore, if you're a cricket, it's only advantageous to stop singing if there are other crickets around you. Okay? Because if not, that fly would still more than likely be able to detect you. And that may be an evolutionary reason why crickets sing in big choruses in the first place, right? It's to spread this parasitic load. So they're the behavioural experiments then. So what the scientists then did is that they put little probe microphones next to those two ears on the prothorax. And they found that as a sound source was moved around them, the ITD changed, the interoral time difference. And this was moved from plus 90 degrees to minus 90 degrees. Now, a technique that was used in this is this thing called laser Doppler vibrometry, which sounds very technical, doesn't it? That's because it is very technical. It's basically used to compare the reflected beam from the reference beam being a laser of light which is directed at the ear. Okay? Don't just know the ins and outs of it, but that's basically how it works, right? And this technique was used to measure the differences in responses of each tympanal membrane to a range of frequencies, and this is shown on this graph here. So we've got frequency on the x-axis and response amplitude on the y-axis. Now, we don't need to worry about the green line for the moment, just focus on the red and blue lines. So, red is one of the tympanal membranes and blue is the other. Now you can see up to 4 kilohertz. There's meant to be a blue line here as well, by the way, but I didn't want to mess up my felt tip pen, so I didn't draw all over the red. But anyway, so the red and the blue are pretty much the same up until about 4 kilohertz. After 4 kilohertz, they start to diverge. The pattern we see is different. Well, that's strange, isn't it? And what's interesting is that this response is very different to the response you get if you put 2 probe microphones next to the 2 ears. Yeah? There, the response amplitude is pretty much the same. So this shows that there's something about the structure of these membranes that's affecting its directionality. It's giving directionality. So the next step was, how the hell is it doing that? So what's the green line for them? Well, the green line was a control. It ensured that the vibration that we were seeing was due to the mechanical coupling and the process of hearing, rather than just the animal vibrating. Okay? Because, you know, look at this pencil. If I introduce a really loud stimulus, it may vibrate a little bit. Yeah? Is it hearing? No, I don't think so. Okay, so that's the control there. And it showed that there was more to it than just the animal vibrating. Which is obvious because we know that they hear, right? These are ears. So therefore we can conclude that these aren't independent receivers. They're mechanically coupled pressure receivers. So let's see how exactly they work. So we've shown so far that the ears on these flies are mechanical processors, right? They're somehow doing something which increases the interaural time difference between the two ears, which increases directionality, right? So now we're going to look into exactly how it does that, and also amplitude is different between the two ears as well. So how is it doing that? Now I've drawn some very scary diagrams here, so let's go through and decipher what on earth this all means. The first thing to get straight is that when you look at these ears under the microscope, they're not flat, right? So it's this which could result in a time delay and an amplitude delay between the two ears, because that means they'll vibrate at different times and at different rates. The first important thing to take into account is that in mechanically coupled pressure receivers, the two receivers are mechanically coupled, right? They're linked. Now what I want you to see here is these two red rectangles are the two membranes, and they're linked, sort of. I've drawn a little red line there to connect them, right? The black lines are those two membranes when they're at rest, when there's no sound playing, okay, when they're not vibrating. Now, if you play a low frequency, then these two sides will vibrate up and down, like that, okay? They'll just resonate like that. Now, that doesn't really give much directionality at all, because they're both vibrating in exactly the same way. They're mirror images of each other, okay? But then again, low frequency, why would a fly want to detect a low frequency? Not really. I mean, the crickets that they want to detect are calling it very high frequencies, so that doesn't really matter. Okay, so that's what we call mode 1, okay? We're using a lot of mechanical engineering terms here, it's very exciting. So, let's see if we increase the frequency so it's higher now. If that's the case, we get into mode 2. We get into a sort of seesaw-like movement where each side is half a cycle out of phase. Yeah, can you see that? Because when that one's up there, that one's down there, so that's half a cycle behind. And in mechanics, we call this a 2-degree of freedom system. Okay, and that's just how it works, right? And here, you can see there is directionality, because the two sides aren't symmetrical, are they? Now, what's even more interesting is that if you go into really, really high frequencies, then things can start to get even weirder. Okay, so this is what we call mode 1 plus 2, or mode 3, I don't know. But anyway, so if you really increase the high frequency, the ear on the ipsilateral side, so the side facing the sound, will be vibrating, as we can see here. But it's going to be vibrating so hard that it's going to cancel out any vibrations on the other side. There's going to be destructive interference. So that means the other side doesn't vibrate at all. So that's absolutely exceptional directionality then. So the contralateral side is silenced by the resonance behaviour on the ipsilateral side, and that's all through due to their connection here on this bridge. Right? And if you do even more physiological experiments, you can see that angular deviations can be detected as small as 1 degree in this species of fly, Olmiocrasia. Well, that is pretty incredible, pretty unheard of as well. So we call this phenomena hyperacuity for obvious reasons. And this is done in a really weird way. It's done by measuring the fly's responses when placed on a rotating ball. So you play a sound from loads of different angles and measure its response by how it turns the ball when it tries to move. Okay, the fly can't move, but its legs can. Okay, so imagine it just dangling there, moving its legs around. Brilliant. Okay, that's the level at the tympanal membrane, but then what if we get down to the neural level? Now, try not to get into too much neurobiology here, but I mean, this is quite interesting, I suppose. So, there's an amplification of the time delay that feeds to the interneurons, those neurons that are going to be transporting these signals all the way back to the CNS. Okay, so that further increases the time delay, so the nervous system has a good idea on where the sound is coming from. So how does it do this? Well, the first thing you do is you take neural readings, right, and then measure the response of these interneurons. And you find that if you start the pulse of frequencies that are similar to that of a cricket, you'll only get one impulse, okay? And that impulse is the first one of when the sound started playing. So this is what you call time stamping, right? This neuron doesn't care about the amplitude, the frequency, or whatever. It just cares about when the pulse started. So you get time stamping. So it doesn't matter how long you do carry on this pulse, that you'll only get one action potential. And that's propagated along the neurons and fed to the central nervous system. And you can plot a stimulus response histogram to show this. Okay? So that's the first point. Now, the next point is that there's an amplitude dependence delay. And this is all to do with the sort of time-intensity trade-off. We talked about how sensory ecology was full of trade-offs. Well, this is one of them. Okay? So, as you increase the intensity of the stimulus, then the time delay decreases. Because for once, you kind of want the sound signal to be late. You want a greater latency because that will increase the time delay. So that means the ear on the ipsilateral side will receive a much louder signal than the one on the contralateral side. And with that, it will receive that signal a lot earlier than the one on the contralateral side. Okay, and accumulating all of this together, then we've now got a time delay which is in the region of milliseconds, not the ridiculous microseconds that we got when measuring, by putting the microphones at the two ears and measuring the time delay then. Okay? So these flies have got it sorted, okay? These ears are so close together on the prothorax of that fly, but it's like they were centimetres apart in the sound field, giving them excellent directionality and making them excellent at detecting those crickets which they're going to lay their eggs on. And that is the end of the story of Ormia acrasia. How exciting. I think it's never had so much publicity. This is a YouTube first, right? This is why you're subscribed. If you are. If you're not, you should subscribe. And on that note, I'll see you next time. Subscribe!